Welcome to this video on vehicle motion modeling. A common problem in emerging automotive technologies is to control the motion of the vehicle. It can be to follow a predefined path or to make an avoidance maneuver. In order to design such controllers, it is necessary to understand the lateral dynamics of the vehicle. In other words, understand how the vehicle behaves when it's steered, either by the steering system or by the propulsion or braking system. To limit the scope a little bit, we will in this video look at planar motion of the vehicle. We will limit the motion to X and Y plane and to study the longitudinal, lateral and rotational behavior of the vehicle. We will neither include pitch, roll nor vertical motion, so we limited our modeling to these directions. Models that describe the planar motion of a vehicle are usually divided into two categories: two-track and single-track models. The single-track model is also known as the bicycle model. We will limit our modeling to the single-track model, and especially the linear bicycle model. The single-track model assumes that the vehicle can be described by only one front and one rear wheel, linked by the vehicle body. So we're actually modeling the vehicle as a bicycle. So for the single-track model, we will have the steering as input and the body motion as output. As we're dealing with a mechanical system, it is suitable to create a free body diagram of the vehicle body to get our conservation law. As we will have both translational and rotational dynamics, we need to use a force balance and a torque balance. There will be one force balance in the X direction and one in the Y direction. To describe the yaw dynamics of the vehicle, we will use the torque balance. So these three equations will be our conservation laws, and they depend on the steering angle and the tire forces via the vehicle body dimensions. So these three equations will be our conservation laws, and they will depend on the steering angle and the tire forces via the vehicle body dimensions. Now we have our conservation laws. Let's continue to the constitutive relations. The forces Fx and Fy are generated through the tires. As we are mainly dealing with the lateral dynamics, the lateral tire force, Fy, is of importance. The lateral tire force is a nonlinear function of the side slip angle, as visualized in this figure. It should be noted that there are many different approaches to describe this nonlinearity. The most well-known is the Pacheco's magic formula. The side slip angle is the angle between the lateral and longitudinal velocity of the tire, expressed in the vehicle's coordinate system. The tire side slip angle for the front tire also depends on the steering angle, so it can be rewritten as this. And the tire slip angle for the rear tire only depends on the tire's velocity, if we do not allow rear wheel steering. If we restrict the model to small side slip angles, only the linear region of the tires are used. This means that the lateral force is approximately proportional to the side slip angle. This restriction is valid up to a few degrees, as can be seen in the figure. Furthermore, the longitudinal and lateral acceleration of the vehicles can be expressed in the vehicle's inertial reference frame, as this. So, now we have a number of equations, and the next phase is to sort the equations and put them into the general state space form. The first step when forming the state space model is to select state variables. We see that we have three time derivatives among our equations: the velocities in X and Y direction, and the yaw rate. So let's choose these as our state variables. Let's start forming the state space model by taking the derivative of the first state variable, the longitudinal velocity. By using the equations and put them in one at a time, we will end up with this nonlinear expression. Let's continue to the next state variables. And if we do the same, we end up with these nonlinear expressions. As these functions are not only functions of the states and the steering input, but also the longitudinal forces, Fx, we can affect the motion of the vehicle with not only the steering, but also with the propulsion and braking system. And this is why braking is used in, for example, stability control systems like ESP. So, this is the nonlinear state space model of the planar motion of the vehicle. We can stop the modeling here if we like, but we will continue to derive a linear single track model. Let's start making some assumptions and simplifications. The first assumption we can make is to assume that we have constant velocity of the vehicle. This results in that the first state derivative is equal to 0, so we can remove that from the model. This is a valid assumption if we go on a highway, so let's add that as an assumption. If we go on a highway, we usually have small side slip angles. So this results in that the tangent of the side slip angle is approximately equal to the angle itself. The next assumption we can do is to assume that we have no longitudinal external forces to overcome, so that Fx becomes 0. This is also valid if we do not accelerate the vehicle, which is one of the assumptions we make. This results in that these forces can be neglected. The last assumption we make is to assume that the steering angle is small. Cosine of the steering angle is approximately equal to 1, and sine of the angle is equal to the angle itself. This affects the model in the following way. If we compactify the model equations, it will look something like this. So, these assumptions have now given us a linear model of the lateral dynamics of the vehicle. It should be noted that the longitudinal velocity is a parameter in this model, and it enters the model both linearly and non-linearly in the model. So, using the three-phase method, we end up with this model. We can, if we like, do a variable change, where x is the state variable, u is the input signal, the steering angle, and y is the output signal. In this case, we have two outputs, the lateral velocity and the yaw rate of the vehicle. With this name change, the model can be rewritten as this. As this model is linear, as we assume the velocity is constant and is a parameter in the model, we can rewrite it in matrix form. And doing this, we end up with the following representation. So, this is the bicycle model or the linear single track model that can be used for studying lateral vehicle dynamics. We should be aware that we, in order to derive this model, made a number of assumptions, so the validity is limited. But it's still very useful, especially if we're going at constant velocity with small steering and side slip angles, which we often do when we're out driving our vehicles. Thank you for watching and good luck with solving the exercises that follows this video.